So now let's talk about how we can use information about f prime to learn about what f is doing. So let's imagine we have this nice parabola here, f, and the minimum seems to be at 13. 13 is just some arbitrary number, of course. What can we say about the derivative of f? So I know that I'm asking the opposite question about what we just asked, but let's practice our skills from chapter 2 of given the function, can we draw the derivative? So go ahead and sketch this out on your paper and then draw the derivative function. So you hopefully paused it and are now back. And you'd say, well, there's a flat tangent line over there. So this derivative would be 0. Over here, the derivative is positive. Over here, the derivative is negative. And I had said this is a parabola. So you know the derivative of a parabola is a straight line, and the straight line's value has to be 0 here, and it has to be positive over here and negative over here. So f prime should look like that. So now that we know the mapping from the derivative, from the original function to the derivative, and seeing that, let's imagine going backwards. So let's pretend we can't see that original function f. All we can see is f prime. So we'll have the same axes as before, but this time we'll only have that function, the f prime. So what can we say about where f is increasing and decreasing? And I know you could look up here, and it's not exactly cheating because I deliberately drew them on the same page, but kind of pretend you can't. What can you say about where f itself, the original function, is increasing? Well, you could say from here on over, so that's on 13 to infinity, you could say, well, you could say use a open bracket there. F prime is bigger than 0, so the original f is increasing on 13 to infinity. What can you say about from here on back, like that? You say basically the opposite, right? F prime is less than 0. So the original f is decreasing on negative infinity up to 13. So here's the tricky part. F prime is negative here, so the original f is decreasing, even though the derivative is increasing on that range. So that's something that trips some people up. They say, oh, the derivative is increasing, so the original function must be increasing. And nope, that's not what's going on here. It is possible for f prime to be increasing and the original function to be increasing, and that's a good puzzle. Can you draw something that works like that? Well, maybe right here. The original f is increasing, and the f prime is increasing, and the original f is increasing. Let's do a slightly harder problem. There we go. So let's draw something like that. -5. And what can we say about, and that's f prime. So test yourself now. What can you say about where the original function is increasing or decreasing? Okay, so where is f, the original function, decreasing? Are you tempted to say, well, look, this is decreasing, and that function is decreasing, but that's not the original f? So some people would be tempted to say, that the original f is decreasing on negative infinity to negative 5 because they see that the derivative is decreasing there. But that's not what we want to say. We have to say f is decreasing where f prime is less than 0, which is on what interval here? It's on the interval from negative 5 outward to the right. So from negative 5 to infinity, that's where f is decreasing, even though f prime, that's where f is decreasing, and even though f prime is decreasing all along, f itself is only decreasing over here. Right, so we could kind of highlight from here on out, f is decreasing. What's happening over here? Here the derivative is positive, which means the tangent line has a positive slope, for example, or the rate of change is positive. So over here, f is increasing, even though it really doesn't feel like it from this graph. So what can we say about what the shape of f is here? The original function. Sketch it in if you can. And there's more than one right answer here, and that's an interesting thing, but sketch in a version of f that matches this graph. Well, you might have said, well, the original function has a 0 derivative here, so it needs to have a flat tangent line. Over here, it has a negative derivative, so our function needs to be decreasing. And over here, now this gets tricky, the original function is increasing, so it has to be increasing like this to meet that point. That point could have been higher or lower, I just kind of picked a point. This is a straight line for the derivative, so the original function should be a parabola. So the original function has to be a parabola that's peaking at that point. Could the whole thing have been higher? Sure, that wouldn't affect the derivative, that wouldn't affect the slope of the tangent line at each point. So we're saying here the tangent lines have positive slope because f prime is positive. Over here they have negative slope because f prime is negative. And this is an f possibility. Other original functions would be the same parabola but higher or lower. Here's a question some people get interested in. What's happening right here? So I'm doing this in a different color. Can you say that f of x is equal to f prime of x, that the function and its derivative intersect? Well, it sure looks like that on the graph, and on some graphing utilities like Desmos, it'll even put a little dot there and tell you the coordinates of that. But it turns out that really doesn't mean anything at all. So let me write that in a different color with a big nope. Remember that the function and its derivative actually have different units usually. Like if f is in meters and the time axis is in seconds, f prime would be in meters per second. Can you say that like 20 meters equals 20 meters per second? Nope, those are entirely different units. That would be saying, that's just as bad as saying like 20 kilograms equals 20 kilometers. It just doesn't work. So f and f prime are usually in different units. Like meters versus meters per second. And in some sense, they shouldn't even be on the same y-axis. It's just that we draw them that way for convenience, and so we can be careful about having the same x-axis. They should have the same x-axis. So don't spend any time talking about where f and f prime intersect, because they don't really intersect. It's just kind of an artifact of how we draw things.